Hello, welcome to Low-sal-life. I am so glad you guys decided to click on the title because obviously it is basically not for the faint of heart, but we're going to make it easy today. We're going to talk about basically an introduction of organic chemistry so that you, as somebody who has allergies or salicylate sensitivity, will be able to look at basic chemicals and decide whether or not it's a risk for you based on it being a salicylate or not. So that's our goal today. We're going to do a little bit different format. I've got some slides that we'll be going through, and I'll be drawing on them just to be able to circle things for you. And I hope that this format works for you and that you're not bored. I don't think it's terribly boring, but some people might think it's over their head, but really I don't think it is. If you've ever put together Legos or puzzles or sorted silverware in a drawer, you should be able to understand the concepts that I'm going to teach you today. Special thanks to ChemSpider for having all of these items available to look at. My goal is that you could feel confident enough to go on PubChem or ChemSpider, those are my two favorite websites to look, and be able to type in a chemical and be able to look at its shape and decide whether or not there is absolutely no risk, or possible risk. So that's kind of how I kind of figure out like what's what. So here's the agenda that we're going to cover, and I have the timestamps down below so you can easily go from one section to another. So we're going to cover what is organic chemistry, what isn't organic chemistry, and then we'll be covering what an aromatic is. I think that one might be interesting for some people. Then we'll cover what a benzene, a phenol, and a salicylate is at its base, its core. We'll look at different salicylate molecules. These might answer some of your questions when you're looking at the food list, be able to understand it a little tiny bit better. We'll look at bound versus unbound salicylates, which a lot of people didn't realize was a thing until I put my food list up and showed different results, like Malacar and Kesica, for example, have different, they provide both a bound and an unbound salicylate. So we're going to just briefly cover what those are, but I will have a video in the future about that specifically. So if you don't want to miss that, make sure you subscribe and hit that bell button, because I may post in a week, I might post in a few months, so make sure that you don't miss anything if you want to see when I post my next video. And then we'll have some examples and a little quiz at the end. So let's get started. So just a reminder that chemistry covers all of the elements in the world and how they interact with each other. So just as a refresher, this is what a periodic table looks like. You can see that they are arranged in a certain order. This periodic table is conveniently colored, so it makes it easier if you're trying to do some equations on your own, but we're not going to do that. I specifically want to look at organic compounds. I find organic chemistry interesting. I am not a chemist, I should say. I am a biologist, but organic chemistry is actually required to get a biology degree. I think I would probably do a lot better now, especially since I'm a little bit more interested in it because of my salicylate sensitivity. But the basics that we're going to cover today are going to be good. So I do want to say that a lot of people use organic, most often related to food and as a positive trait. Organic doesn't mean that in the science world. So organic means basically having a carbon backbone or being made of carbons. Is basically the backbone of life. We cannot exist without organic chemistry. Our tissues and our bodies are made out of carbon atoms, and more so than any other element. So that's something to think about. I guess maybe water could be argued, but organic does not imply healthy, even though we associate it with life. It does not imply healthy. it actually, there are plenty of organic compounds that can harm you. And so I will have some examples later. To the very basic definition, organic chemistry must require covalent bonding. And we're not going to go into that at all, but just know that there are two types of bonding. There's a covalent and another one, which we'll talk about in a moment, just so that we know that there's ionic bonding. Couldn't remember it. Just to know that there's at least those two types of bonds. Here's an example of a couple of organic compounds. So the one on the far left, I actually had to trim it off because it was really long, but that's the main portion of chlorophyll B. This is the green energy store of plants, and you can see that it's a very complex molecule with lots of lines and shapes and N's and O's, and that is an example of an organic compound. And that one you can eat, and it's probably good for you. The second one is methanol, and this is the I think this is probably the smallest organic molecule, but it has one carbon in the center, and it's got the hydrogen bonds and an alcohol bond, an OH bond attached to it. So that one only has one carbon, so not exactly a carbon backbone, but still it uses covalent bonding, so that's why it's part of organic chemistry. You can go up to octanol, and that one you can guess that oct is 8, but if you wanted, you could count it 1, 2, 3, 4, 5, 6, 7, 8 with an alcohol group at the end. So I don't recommend consuming methanol or octanol because those are poisonous, but they are also organic. So just kind of throwing that out there that this isn't just organic is not good for us. Or natural. There's plenty of fossil fuel organic products. So just putting that out there. This last one is a monounsaturated fat. All of our fats are organic. And this one here, you can see we've got several carbons, 1, 2, 3, 4, 5, 6, 7 carbons on there. And then all the hydrogens are spelled out. You don't have to show all the hydrogens when you're looking at them, but this one here is they just broke it out for us so that we knew that there were at least hydrogens there. Our next slide is going to be about symbolizing organic compounds. So we could certainly do organic compounds in a formula. So that's one of the basic ways to talk about a chemical. One thing about formulas is that it doesn't give us any information about the shape, and that may or may not break a compound as far as it being bioactive or bioavailable in the body, or basically different shaped compounds can do different things. So, but if you want to know what the very basics are, the formula is a good place to start. Okay, so we'll stick with octanol because that one's really simple. It doesn't have anything fancy on it, right? It's just a line with an OH group at the end. So if we were going to write this as a formula, we would write it as C8H18O, meaning it has 8 carbons, 18 hydrogens, and 1 oxygen. So that would be how it's written as a formula. Here is a version of what it looks like as a 3D shape. Generally, every molecule, every element has a different color, so that's helpful when you're looking at that. Here is an example of it written out with letters and lines. So in this case, we're looking at we've unpacked what we saw on the last slide. We've unpacked it and just showing every single element present and every bond. So here we have all of your carbons, you have your hydrogen, and you have your oxygen. If we recall from the monounsaturated fat from the slide before, you can see that there is a double bond on here, so that is marked with 2 lines. A single bond has 1 line. And then we can also not show the hydrogens. That we can kind of count how many hydrogens there are once you get really good. So you can just show it as a shape. So here, every single corner, every little point we can assume that there's a carbon at that point, and then we can also assume that there are hydrogens. So the big thing with carbons is that they have the capacity to have 4 bonds. So in some cases they'll have a double bond, but wherever there isn't a single or a double bond represented, like in the line, we can assume that there is a hydrogen in its place. Here's an example of a salicylate, and you can see that there are points on the hexagon. We can assume that there is a carbon there. So you have 6 carbons in that little ring. You have some lines that are single, which imply a single bond. Some lines are doubles, and those are double bonds. And then you have the OH, so we can assume that the oxygen is the next point, not a carbon. And then on the other side, you can also see that there's like a little minus sign, and that means that there is the ability to add a hydrogen or another bond, but in this case, it's not represented. So that might mean that it could function freely as an ion, which we won't get into today, but basically there is the capacity for an H there, or maybe attaching to another carbon or something like that. And then just one other thing, when you see this hexagon, this is a benzene ring when it has those 3 double bonds inside, and it can also be represented with just a circle in the middle. So if you ever come across anything that just has a circle inside, it's just a faster way rather than being really precise and drawing in the double bonds. So that is the same symbol for a benzene ring. All right, so now that we've talked about what organic chemistry is, basically a carbon backbone, you have covalent bonding, and it can be represented by a lot of different symbols, but mostly lines. Next, we're going to talk about inorganic chemistry, and just very briefly. And basically, I want to cover that it is basically everything that is not organic chemistry. So when you're looking at a periodic table, if you basically cross out carbon there, that's what the rest of inorganic chemistry covers, everything else. Now, there are some cases, I wrote a couple down here, where there is carbon dioxide, CO2, carbonic acid, H2CO3. Those are carbon molecules, and so they could be confused for organic chemistry, but they actually use ionic bonding and not covalent bonding. So that's the reason why they're in this camp and not the other one. Common items that you might come across that are also inorganic are sodium chloride, NaCl. This is your basic table salt. Sulfate, SO4, so that's sulfur with 4 oxygens, or ozone. It's just 3 oxygens. So those are all types of inorganic chemistry. So when somebody asks me if, like we were looking at lipstick last week, and I mentioned that barium sulfate is definitely not a salicylate. Well, how can I be sure? And the reason why is because that is an inorganic compound. It doesn't contain a carbon, and we can be really sure that that's not a salicylate. So here are some examples of inorganic compounds. The first is NaCl. It's basically just your plain old table salt. Potassium chloride is like this too, where you have 1 sodium molecule and 1 chlorine molecule. They get together through ionic bonding. They actually dissociate in water, so they kind of are free floating in water, but when they are dry, they become a solid and attached to one another. Calcium chloride is another one. This is a calcium element with 2 chlorine elements. I believe calcium chloride is used in vitamins and supplements, I want to say, and maybe some food preservatives. I do also want to say that just because it's inorganic doesn't mean it's healthy. I'm just saying they're not salicylates. So mercury is on here, and so is lead. We all know that those are detrimental to human health. when consumed. So this argument is not that everything on this periodic table is good for you. It is just an argument that they are not salicylates. Okay, the last thing is the nitrate. Nitrites and nitrates are natural, and they could be synthetic food preservatives. They could be, like for example, they're in celery naturally. Nitrate is just nitrogen with 3 oxygens, and this is what the shape looks like. Yeah, so there you go. Nitrates and nitrites, I can confidently say, are not salicylates. They don't have any carbon. They don't have the shape of a salicylate. They don't use the same kind of bonding. All right, we're gonna move on. Okay, heading back to organic chemistry. Now that we know what is organic chemistry, we know what is not organic chemistry, and now we're gonna go dive in a little bit more. All right, in organic chemistry, there is something called an aromatic. Basically, this I want to bring up first because it's the basic structure of a salicylate, but it also, like organic, means something casually or when related to money, but scientifically it is rarely used correctly, right? Organic does not mean good for you or natural. Aromatic does not have anything to do with odor or fragrance. As a matter of fact, there are plenty of aromatic compounds that have 0 fragrance. Aspirin is an example of one. So let's look at a couple here. An aromatic, also we're not going to go into this, but there are certain criteria that go into this, but basically we're looking at a carbon ring. It can be 5 carbons, it can be 6 carbons. I think I saw some that had a lot more. And an aromatic can contain all carbons only, or it can contain maybe some nitrogens or some oxygens in there. And I'm not going to go into this very much, but here are a couple of shapes. The first one is a simple aromatic. This one's called furan, and it's got 4 carbon atoms and an oxygen. So a little bit different shape. Here, benzene, this is the one we're going to focus on today. This one has 6 carbon atoms with 3 double bonds. This is called a benzene ring. Benzene is it is aromatic in its pure form like this. So it is, we'll say, odorous. The next one is a fused ring. So basically you have 2 benzenes attached to one another, but naphthalene, this is 2 benzene rings attached. That is another example of an aromatic. You have fused rings together. Okay, another thing that we're going to talk about in organic chemistry is functional groups. So basically you can have a base molecule and they can change based on the functional group attached to it. So that's kind of where we're trying to get to. What is the base salicylate molecule and how does it change? Because there's lots of different forms, and that's what makes it really hard. I want to talk about 2 that are really important, and the last one I thought you guys might like because I know a lot of you guys are amine sensitive. So the first one's called an alcohol group. This is just an OH group. This picture here that I drew shows the extra electrons that are available. Basically, you can draw it with just an OH in the diagram, and that implies an alcohol group. The next one is a carboxylic acid group, and that's the COOH. So we have the implied C in the middle. We've got the double bond to the O, the oxygen above, and then we have a single bond to the O with an H on there. So that's a COOH, and that is basically an acid. You can call it an acid, but it's specifically carboxylic acid. And then the last one, anytime you attach a nitrogen with a pair of electrons, you get an amine. So here, this is kind of funky how it's written, but R stands, it's basically like a variable. It stands for the rest of the chemical structure. So you can put whatever you want in there as long as it has a nitrogen and a double a pair of electrons, that's what an amine is. All right, we're just about done with the lesson, and then we're going to look at some examples. Next, we're going to look at the 6-carbon aromatics, specifically the benzene rings. These are interesting to us because they make the base of a salicylate. So the first one, it should look familiar to you. You have the benzene ring. You've got 6 carbon atoms. You've got 3 double bonds, and you have implied hydrogens in there that aren't being shown. If we attach an alcohol group to this, it automatically becomes a phenol. So some people in the food sensitivity world say that they're sensitive to phenols. I think that that's a little bit of a stretch, but it is broad enough that you're going to probably cover everything that you're sensitive to. I think it's a little bit too broad. But that is when people say they're phenol sensitive, that is what they're talking about. Okay, the last one is the salicylate. So you have your benzene, you basically have your phenol, right? You got your alcohol group attached to your benzene. And then you also have a carboxylic acid, that's COO, attached here. COO. This might have this one in particular says minus because they took the hydrogen off. So this could essentially, it makes it active. But there could be an H there too. So that's your carboxylic acid on there. And so we're going to move on to different salicylates in particular. So this first one is salicylic acid. So you've got your benzene ring, you've got your alcohol group on there that makes your phenol, and then you have your carboxylic acid on the top, the COOH. This is what all the reports show on our food list. They report it in either, in usually milligrams of salicylic acid per kilogram of food. And I did note that that one in particular is odorless. You can look on ChemSpider, and there should be attributes down below where it says whether or not it's fragrant or not. And then also whether or not it has color. So that's something that can be helpful. For example, I was on a forum and I noticed that somebody was really mad that their vitamin Bs had yellow dye added and it wasn't in the ingredient list, and they would have never purchased it if it was had a dye with it. The reality is that B1 actually is yellow in color. So if you wanted to double check that yourself, you could go to ChemSpider, pull up, or PubChem, one of them, pull up the formula, the molecular formula, and then in the details it should say if it's odorless, if there's an odor, or if it has color and some of those chemical properties. So that's super helpful. All right, so here you can see this is the same as the former salicylate, except it now has the H represented, meaning that it's a full carboxylic acid attached to it, the COOH, and that's what gives the acid portion of the salicylate. But essentially, you still have your base salicylate molecule there. Here is acetyl salicylic acid. You can see that it's much more complex, but in this one, you still have the COOH attached on the there on the right. And then on the left here, you have, instead of an OH, you now have an O attached to a whole bunch of other stuff. So that's going to be the, probably, I'm guessing, acetyl group. And this is aspirin. And then the last one is wintergreen oil. So this one here, you have your alcohol group there. And then you have your COO group. And remember I said that there was a minus sign earlier on the salicylate. So that means that there is a capacity for an H there to make it a full carboxylic acid, a full COOH. But in this case, the H is replaced with another carbon, and then of course there's going to be hydrogens off of those. And that one is very odorous, wintergreen oil. Okay, the last thing we're going to talk about is bound versus unbound salicylates, and this is a really loaded question, especially since I've started posting reports like Malachar and Kezica that they have tested both bound and unbound salicylates. This quote at the top was from Malachar, and this is, they specify that they are using phenolic glycosides and carboxylic esters. So that is what they're considering for bound salicylates. Basically, we don't really know what the difference between them, in the body. Like, you know, I kind of think about like if you're a single person or if you're married, right? As a single person, you can certainly go around and travel easily, and it's easier to get one ticket, and it's easier to, navigate as a single person. Where if you're married or if you're taking a family of 5, right, it's going to be harder for you to navigate. So you can kind of think about it like that. One thing that we don't know is how long it takes for these bound salicylates to break down in the body. Like it could take, let's say, 1 to 3 days. I'm not saying I know that for sure. I'm just saying, what if? If that were the case, then maybe the bucket theory isn't true. And maybe it's just bound salicylates that are taking a long time to unravel in your body are causing problems later on in the day or a couple of days, rather than like a dose theory. So that could possibly be a problem. We don't know very much about it. So, well, I should say we don't know very much about it as far as what happens in the body. So I picked out salicin. So this is a compound from willow bark and populus. So salicin comes from the Salicylates family. It's actually a plant that I study, oddly enough. And salicin here, you can see that on the left I showed you the salicyl alcohol, which is the base molecule. You can kind of see here where you can pick it out. And then the other portion, all these OHs, and it is a ring of carbons with an oxygen. I don't know if that is an aromatic or not. I didn't do the, see if it fits the test of criteria, but you have all of these OHs on there. This is actually a sugar molecule. This is glucose. I think it's D-glucose specifically, but it's just a certain shape of sugar. So that is a sugar molecule attached to a salicyl alcohol. Now this one here probably, even though it's bound, it actually probably digests very quickly in the body because sugar is very water soluble. So it's possible that this is something that breaks up quickly. I'm not sure what that that area where the O is, how easily that breaks up. But I do know that people use willow bark for medicine, so I'm guessing it can't take too long to digest in the body. So anyway, so that is what a bound salicylate looks like compared to an unbound. And of course, I will, as I learn more about these, I will obviously do a video on these in the future. Maybe I'll pull up 10 different examples of bound salicylates, and we can look at them in a little bit more detail. All right, and now the test. You win, regardless if you get the answers right, especially if you're still here. The first one that gets brought up a lot is whether or not nitrates or nitrites are salicylates. Now, I am in no way saying that they are healthy for you. They can both be a synthetic compound or a natural compound. Celery is a great example of natural nitrates. Bacon, usually in order to cure meats, we add these molecules. And you can actually be sensitive to nitrates and nitrites. If you're already salicylate sensitive and let's say, gluten intolerant, it's not terribly unlikely that these might cause you problems. It's possible, but we're looking at a salicylate viewpoint only. So let's look at the two that I pulled up. I have NO2 minus and NO3 minus. And these here, nitrite and nitrate, oh, I did those backwards on the, so these two, these form ionic bonds, and so they also don't have carbon. So in these cases, these are not organic compounds because they don't have carbon and they're not covalently bonded. So in those cases, these are inorganic compounds, meaning that these are not at all anywhere close to a salicylate. And also you can just look at them. There's no benzene ring in there, so we don't even need to blink twice. Just because I said it's an inorganic compound does not mean that it does not occur naturally in nature. Again, the celery is an example of that. This is one that I get often, oxalates, because anybody that explores salicylate sensitivity probably also explores amine or oxalate sensitivity. And oxalates are in coffee, decaf coffee, they're in chocolate, they're in a lot of foods that I eat, and everybody asks me if I'm oxalate sensitive or if I watch that. I do not react to them at all. Now here are some diagrams of oxalates. You can see they have carbons. They've got their carbon backbone, right? They've got 2 carbons in there. In some cases, you might have a ring there. I don't know if that's an aromatic ring or not, but there is a ring of carbons and oxygens and magnesiums and calciums and different things. But basically, when I look at these, I say, okay, they are an organic compound, check. They are also containing carbons, check. But I don't see any phenols in here, any benzene rings, and so this here cannot be a salicylate. This is one that gets asked often, citric acid or ascorbic acid. Now, there is the possibility that these are derived naturally. You can see that this picture here even puts a lemon on there. We know lemons are high in salicylates. So it's possible, if it is not refined enough, that it could have some natural botanicals in there, and those could contain salicylates. Citric acid and ascorbic acid are usually so refined, and even ARPA says that they're fine. In its purest form, they are not a salicylate. You can look at it. Obviously, we've checked our boxes here. We've got carbons, plenty of carbons in there. Check. We've got, which means it's organic. We have no benzene ring in citric acid. You know, looks like it could be close, but it's not. And then also for ascorbic acid, you have a ring there, but it's a 5-sided ring with an oxygen in it, so pretty far away from a benzene ring. So these here are not a salicylate in any way, shape, or form. This is another one that people ask about, is magnesium stearate. It's available, they use it a lot in supplements. I don't know what the purpose of it is in supplements. I feel like maybe an anti-caking agent. Oddly enough, magnesium and calcium stearates are soap scum. So, you know, super fun. You can do whatever you want with that. But in small amounts, it's supposed to be well tolerated. So here, this one is kind of funny, weirdly represented, but you've got the magnesium there on the left, and then you have your 2 oxygens with your minus. So those little 2+ and those little oxygen minuses, those are going to hook up and essentially marry each other. And then you have these long chains of carbon and really nothing else on there. So these here, there is no benzene ring on here. Yes, it is a organic compound, but no, it is nothing like a salicylate. All right, I'm moving on to tricky things. So here are 2 compounds. These look super tricky. They have a benzene ring, and they also have a phenol on there because they have the OH. Now, I'm not entirely sure what this other OH does to make it not a salicylate or dangerous for us, but we have, these are not salicylates. I'll show you what they are. The one on the left is dopamine, and the one on the right is an adrenaline, noradrenaline or norepinephrine. These here both are manufactured or created by your body naturally, and they are needed for everything that you do. So they are They look kind of shady with the tools that we have, but they are safe. Of course, I don't recommend too much adrenaline at any one point in time. Obviously, you can get really sick if you have too much adrenaline. So, but I'm just saying it's not a salicylate, but it kind of looks like one. All right, moving on. This one comes up a lot, and this is kind of, I think, kind of that idea of you're allergic to phenols. But this one, these are benzoates or benzoic acid. There's sodium benzoate is another one. But the one, basically you've got a benzene ring and that acid on there. And that is possibly something that could make you sick, but it is not a salicylate. I'm not saying that it can't, the thing about salicylates is that it unlocks a key in your body. Right, it functions as a key and it unlocks something in your body so that you have a reaction. I'm not saying that benzoates or benzoic acid can't do that, but it really needs another oxygen on there in order to, be a salicylate, but it's pretty close. So with that one, I'm gonna say, I don't know. I can tell you it is not a salicylate. It is treated differently as benzoates, but it could be something that could cause you problems. So, keep an eye out for that if you get something like a medicine or I see them in cosmetics sometimes, benzoates. So I've still experimented with these. I've had some food products that use it as a preservative, and I haven't had any issues with it, but doesn't mean that you might not. And then let's look at a couple of dyes. So a lot of people are concerned about dyes, both naturally occurring or synthetic. I like to make eyeshadow and makeups and different things like that. And so I wanted to look up some of the colorants that I use. So these here, the ones on top, we've got manganese violet. You can see that there is manganese on the left. You've got your, I think those are phosphorus, your P's, and then you have your, some kind of like ammonium group. But you've got all of these things here. None of these have a carbon in them. They use ionic bonding, which is why they have the little pluses and stuff. And they do not do there's no carbon in here, there's no covalent bonding, there's no benzene ring, there's no chance that this is a salicylate. So if you found a makeup that you liked, but it had this in it, this should probably be okay for you. Here is iron oxide, iron 3 oxide, and iron 2 oxide. These are basically just iron with oxygens. So that's the little Fe symbolizes iron. You've got your oxygens there. You've got double bonds, single bonds, and these again are nothing close to a salicylate. Now this one here, I thought I'd throw it in there because it came up with colorants and dyes, and people use curcumin for dyeing things yellow. Now, curcumin is from turmeric, but turmeric is not this compound only. This is the active ingredient in turmeric. So here you can see that there are 2 very questionable compounds in here, and these look like salicylates to me. I'm gonna have to break it down just a little bit more. I'm not sure what that oxygen with a carbon on the end, what it could look like, but this could very well be an example of a bound salicylate. You've got this middle molecule in the middle, and then you've got these 2 phenols on the end that look a lot like salicylates, and this very well could just be a bound version. Now, we know from former studies that they show up very high. Just Malakar's study at 38.83 milligrams per kilogram is very high. This is for turmeric, this isn't for curcumin, but it's still in the very high category. All right, that's all I've got for today. Let me know, I'm afraid to say, let me know if you have any questions down below. I will try to answer them the best that I can, but basically I just want you guys to feel a little bit empowered that you can look up a molecule on ChemSpider and have an idea for, yes, this is absolutely not a salicylate, and this here looks questionable. I'm gonna be a little bit more cautious on that. So I wish you the very best. Thanks so much for sticking it out to the very end. I really hope that this information was helpful and maybe even liberating, and I wish you the very best in your low salicylate journey. If you found this content valuable, don't forget to like and subscribe. And also you can find me on Instagram at Low-sal-life. All right, take care. Bye.